Think for a moment. You're alone on a dark street. A shadow approaches, breaking the silence of the night. Your heart begins to pound as if it will burst out of your chest. Your breath catches and the blood drains from your face. In this moment of panic, what happened first? Did you feel fear and then your heart rate accelerated? Or did you realize you were afraid because your heart began to pound?
This simple question launched one of the greatest mysteries of humanity and science, the field of affective neuroscience. On this breathtaking 2,000-year scientific journey, spanning from ancient Greek philosophers to modern artificial intelligence labs, we will discover how our emotions are programmed in the brain's hidden circuits, why the amygdala dominates the brain's fear map, and just how flexible our emotions truly are.
Are you ready? Then let's begin this seismic journey of discovery. Our story starts with the first philosophical whispers, a 2-millennia quest starting with whispers. Today, we pursue perhaps the deepest mystery of what it means to be human, emotions. Where in the dark corridors of your brain do your anger, joy, or that heart-wrenching sense of fear come to life? This journey is not new. Its origins go back over 2 millennia to Socrates, who whispered that phobos, fear, and deos, dread, concern the expectation that something bad is going to happen. However, back then, emotion was merely an abstract topic pursued only by philosophers. After the Renaissance, great thinkers began to look behind this abstract curtain. Spinoza, for example, classified emotions into just 3 primary types: desire, joy, and sadness. David Hume assigned a servant role to reason, famously stating, "Reason is and ought only to be the slave of the passions." Simply put, our emotions guide our reasoning.
2 seismic shifts and the birth of science. Our story was shaken by an intellectual earthquake in the late decades of the 19th century. The first tremor came from Charles Darwin in 1872. In The Expression of the Emotions in Man and Animals, Darwin attempted to characterize several basic emotions, noting their overlap across species. Darwin stated that even when emotions are slightly felt, our whole system is nevertheless disturbed, sowing the seeds for affective neuroscience. Immediately following was the second great upheaval from William James in 1884. James postulated a different sequence for emotion. Traditionally, we say, we meet a bear, are frightened, and run. James proposed the opposite. Bodily arousal is experienced first, and emotion follows. For example, we feel sorry because we cry, angry because we strike, afraid because we tremble. Our feeling of those bodily changes is the emotion. This idea, combined with Carl Lange's independent observation, created the famous James-Lange Theory of emotion, which was a major step in integrating physiology, like arousal, with psychological phenomena.
Journey to the brain center, Cannon, Bard, and the Limbic System. In the early 20th century, physiologists began looking into the brain's core. Walter Cannon criticized the James-Lange Theory, noting that the same visceral changes occur in very different emotional states and non-emotional states. Cannon and Philip Bard both proposed that the central nervous system was fundamental to emotion. They argued that both arousal and the feelings of emotion occurs simultaneously, suggesting the thalamus and hypothalamus were critical to emotion. This was dramatically supported by Walter Hess, who showed that electrical stimulation of the hypothalamus caused rage or fear in cats. But the person who truly mapped this area was James Papez. In 1937, he put forward his influential theory proposing that emotions are represented in a set of interconnected regions that include the amygdala, hypothalamus, and prefrontal cortex. Paul MacLean later redefined this circuit as the limbic system. These anatomical models established the foundations for modern affective neuroscience.
The cognitive revolution and the two-factor theory. By the 1960s, psychology moved swiftly away from behaviorism, which had largely ignored the brain and emotion. This transition gave way to the cognitive revolution. At the forefront of this new frontier were Stanley Schachter and Jerome Singer. In 1962, they proposed the two-factor theory of emotions, which postulated that our emotions are plastic and that the emotional experience is determined by cognitive factors. They hypothesized that when subjects felt a bodily state of arousal, like an increased heart rate, for which they had no explanation, they would look for explanations for the arousal and thereby label the emotion. They showed that context became important in these explanations. This model became the foundation of modern theories of emotional construction.
The rise of the amygdala and the clash of contemporary theories. From the 70s to the 90s, a new generation of neuroscientists began asking how the brain represents emotion. Throughout these studies, one brain region began to dominate the landscape, the amygdala. Building on earlier work, researchers like Joe Ledoux showed that the amygdala was involved in conditioned fear, while human studies showed its significant role in the perception of danger. Bestsellers like Ledoux's The Emotional Brain, 1996, and Antonio Damasio's Descartes' Error, 1994, brought affective neuroscience to a larger audience. The last 30 years have seen an emotional enlightenment, accelerated by the increased use of human brain imaging. Today, we see a theoretical explosion. Innate emotions, Jacques Panksepp, early 80s, proposed a set of primary emotions, such as fear, rage, and joy, suggesting they were genetically programmed in subcortical circuits. Emotional construction, Lisa Feldman Barrett's radical theory, suggests emotions are part of a single dynamic system that configures emotional states through prediction rather than stimulus responses. Dual versus single systems, Ledoux and Pine proposed a two-system approach, a defensive survival circuit plus a cognitive circuit for conscious fear feelings, while Fancelot and Pennington support a single unitary model, a central fear generator. The threat continuum and new tools, computational ethology. Affective neuroscience now studies survival behaviors through the threat imminence continuum model, which proposes 4 levels of danger. 1. Safest position. No potential for predatory danger. For example, a lizard in its underground nest. 2. Pre-encounter threat. No threat is present, but an encounter is likely. The goal is detection and avoidance, leading to behaviors like intermittent locomotion, pauses in movement, and thigmotaxis, staying close to edges. 3. Post-encounter danger. The threat is present, but there is no interaction. For example, the lizard spots the predator, but the predator hasn't spotted it. This often results in freezing or flight. 4. Circa strike phase. The predator detects the prey and begins to attack. The prey enters escape mode, using strategies like protean or zigzagging movements. To understand these dynamic behaviors, the newest tool is computational ethology. This field allows for precise neural recording in free-moving animals and uses unbiased machine learning approaches to measure dynamic behavior such as effects of proximity to danger. The great unanswered questions. Despite these discoveries, affective neuroscience still faces massive questions. Why do we see such an overlap in neural circuits associated with different emotions? How does the brain integrate information across autonomic, cognitive, and conscious systems to produce a unified emotional picture? The semantics of fear and anxiety. Fear is generally defined as the emotional state when the danger is present, here and now, while anxiety is about distal or future threats. Yet even leading scientists show many discrepancies in their definitions of these emotions. The comparability problem. Animal models are often limited to behavioral and autonomic responses, making it impossible to ask them how they subjectively feel. Human experiments, on the other hand, are limited by tools and ethics, creating a large gap in measurement across species.
Finally, where do we go from here? As we engage more with artificial intelligence, how will it affect human emotions? Can AI guide or even stop negative emotions before they are consciously experienced? And how does the virtual world change our perception of others' emotional states? Affective neuroscience is living through an age of affectivism. The veil over our brain's emotional map is slowly being lifted. This exciting story is only just beginning. Which emotional circuit in your brain do you think determines your survival the most? Share your thoughts in the comments.
I truly enjoy sharing topics like this from the world of cognitive science with you. Your support is invaluable for us to continue this journey of discovery with a curious mind. If this video gave you a new perspective, don't forget to hit the like button and subscribe to the channel. Always stay curious.